are two nuclear processes that release enormous amounts of energy. You have already learned about nuclear fission. It is a process in which a heavier nucleus splits into two lighter nuclei with the release of a large amount of energy. Now, you will study about nuclear fusion. In the nuclear fusion process, two lighter nuclei combine to form a heavier nucleus, releasing a large amount of energy. For example, when two hydrogen nuclei, that is, protons, fuse together, a larger nucleus of deuterium is formed. In this process, a large amount of energy, approximately equal to 0.42 million electron volt, is released. Similarly, when two nuclei of deuterium fuse together to form a nucleus of helium, energy equal to 3.27 million electron volt is released in the process along with a neutron. Two nuclei of deuterium can also fuse together to form a nucleus of tritium, releasing an energy equal to 4.03 MeV along with a proton. In all these nuclear fusion processes, we see that two nuclei combine to form a heavier nucleus. We know that the nuclei are positively charged, and as such, the nuclear fusion process occurs only when the nuclei overcome the Coulomb's repulsive force between them and come close enough to be within the range of the attractive nuclear forces between them. The Coulomb's repulsive force is referred to as the Coulomb barrier, and the height of this barrier depends on the charges and also on the radii of the two fusing nuclei. If two protons, that is, two hydrogen nuclei, should fuse together, the barrier height is about 400 kilo-electron volt. This is a very huge amount of energy. To overcome the Coulomb barrier, the required energy is obtained thermally, that is, by raising the temperature of the proton gas. Let the temperature of the protons be raised to T to obtain energy of 400 kilo-electron volt. We know that the energy gained must be equal to 3 by 2 kT, where K is the Boltzmann's constant. Substituting the value of the Boltzmann constant and simplifying, we get temperature T equal to 3 into 10 power 9 Kelvin. Therefore, the temperature of the protons has to be raised to this value, so as to enable them to overcome the Coulomb barrier by thermal motion alone. This process is called thermonuclear fusion. Let us now consider the Sun's core, which is at temperature of about 1.5 into 10 power 7 Kelvin. But it is observed that protons fuse together in the Sun, even though the temperature is 100 times lesser than what is required for the protons to fuse. The reason for this puzzle lies in the fact that 3 by 2 kT represents the average kinetic energy of the molecules. But then, there are some nuclei which have kinetic energy more than the average values, and such nuclei overcome the Coulomb barrier. Therefore, we see that the Sun's core has extreme conditions of high temperature and high pressure to enable the nuclei to fuse together. Such thermonuclear fusion reactions occur in the Sun and other stars and form the source of the enormous amount of energy of the stars. We know the Sun has been a source of energy for us. over the past 5 into 10 power 9 years, and estimates show that this can continue for the next 5 billion years. Obviously, the fusion reaction taking place in a repetitive cycle forms the source for such continuous energy generation. In the nuclear fusion process taking place in the Sun, hydrogen nuclei fuse together to form the heavier helium nucleus and in the process release enormous amount of energy. This is a multi-step process and is called the proton-proton cycle of nuclear reactions. In the first step of the proton-proton cycle, two hydrogen nuclei fuse together to form a deuteron releasing a positron and a neutrino along with energy. The deuteron formed in the first step fuses with another hydrogen nucleus to form a lighter helium-3 nucleus releasing gamma rays. In the last step of the process, the helium-3 nucleus combines with another helium-3 nucleus to form a stable helium-4 nucleus along with two hydrogen nuclei releasing energy in the process. For the last step to occur, the processes represented by equations 1, 2 must occur twice. The net effect of the above multiple step process is that 4 hydrogen nuclei fuse together to form a helium nucleus releasing 2 positrons and gamma particles along with energy equal to 26.7 million electron volt. This process is estimated to run in the Sun's core for about 5 billion more years, by which it would mostly contain helium nuclei. Then, the Sun's core will begin to cool down and the Sun will collapse under its own gravity. In this phase, the Sun will be called the red giant. If the temperature of the Sun rises again to 10 power 8 Kelvin, then helium nuclei can fuse to form carbon. As the star evolves further and becomes hotter and hotter, other elements with more number of protons can be formed. But we must note that the elements more massive than those which are near the peaks of the binding energy curve cannot be formed by further fusion. The first thermonuclear fusion reaction occurred on the Earth by the explosion of a nuclear fusion device, and energy equal to about 2.6 into 10 power 29 million electron volt was produced in the process.